today we're gonna be evaluating this beautiful monster from the UNSW integration bee. So this improper integral from 0 up to infinity of the sum that starts from this floor of x up to infinity. It goes of 1 over to the power of n times n plus 1 dx. So how are we supposed to solve it, especially with this floor of x in this sigma subscript? Well, let's first of all think about what the floor function even is. So, well, the definition says that it is a function that just brings a positive real number to the closest integer value that is less than or equal to that real number. And so if I were to graph it between 0 and infinity, because those are, well, the only values of x we really care about here, as our integral is actually going between 0 and infinity, well, what we would get is between 0, taking 0 into this interval, and 1, not taking 1 to this interval into this consideration, I'm going to have the floor of x being equal to 0. Yeah, I'm going to maybe mark my axis. Oh, square root, it's going to be y, yeah? Then, between 1, it starts with 1 taken into the interval, and it goes to 2, but excluding the 2 from the integral, it's going to take the value of 1, yeah? So, for example, the floor of 1.7 is going to be a 1. The floor of 1.8 is going to be a 1, and all that stuff. Then, when it comes to 2, yeah, that's going to be the value of 2, is going to be the value of 1. We're going to get the floor having the value, or maybe rather just splitting the value of 2 until it gets to 3, and so on and so forth up to infinity. So this is going to be our, what the hell is it with the square root of x? Yeah, this is going to be our floor of x. I definitely did make a too big of a y-axis there. Yeah, so we see that all those intermediate values that are between integers, yeah, they got brought down to an integer value. So, well, it would make sense to just kind of split this entire interval that I'm integrating over into sub-intervals of length 1, yeah, probably starting and then ending at some integer value to just, you know, get the sense of what this floor of x will be. So I could just rewrite this entire thing as a barrage of integrals. First of all, between an integral between 0 and a 1, yeah, so the first integral, of this sum as n goes from the floor of everything between 0 and a 1, excluding the 1, but it doesn't really matter. Well, there's going to be a 0, so from 0 up to infinity of this 1 over 2 to the power of n times n plus 1 as dx. Yeah? And then the second integral between 1 and 2, the second interval. Now everything under the floor is going to be brought down to a 1, and so our sum is going to start with n equal to 1 and it's going to go up to infinity. There's going to be, once again, of 1 over to the n plus 1 dx. Lovely. And then maybe I'll move it a little bit to the left. We're going to get, that was not my idea, that was not my plan to do it, yeah. Yeah, now it's better. Now I can write the third integral between, now it's going to be 2 up to 3 of the sum that goes from n equal to 2, everything is brought down to a 2 of 1 over 2 to the n times n plus 1, that's all going to be dx. And, you know, it's going to be so on and so forth up to infinity. I hope you guys see the pattern already. So, well, this thing is something we can evaluate. I mean, all of those sums are just gonna be, well, some numbers, I mean, provided it will converge, but I think it's pretty clear that those sums are gonna converge. You can use pretty much every single standard convergence test to prove it. And so we will be able to just kind of took each and every one of them outside of those integrals, because, well, those are just constants with respect to x. There's, well, no dependency on x anymore inside of those sums. So let's go on and do it. We're gonna first of all, well, copy those sums because I'm too lazy to write them down once again. I also value your time too much for that. Yeah, and then we're gonna multiply those sums by just the integrals between 0 and 1 of just 1 times dx. Yeah, so just 1 dx. Then the second integral is gonna just become the sum that I'm integrating there. yeah, but multiplied by the integral on the respective integral between 1 and 2. I'm gonna add it. It's gonna be dx. I'm gonna multiply by that sum, and then once again this guy over here, I'm gonna copy it, I'm gonna paste it. Yeah, it takes a lot of time as well. It does take a lot of time too. Yeah, now it's gonna be an integral from 2 up to 3 of dx times that guy. It's gonna be plus here, and dot dot dot. We're gonna be doing that up to infinity. Yep, lovely. But now, how do we evaluate those integrals? Well, those integrals are just, well, integrals of 1 between 0 and 1, or rather just between consecutive integers. So we see that the integral between 0 and 1 of dx is just going to be equal to x between 0 and 1, but that's just 1. Now the integral, the same look integral, but between 1 and 2 of dx is going to be x between 1 and 2. That's just gonna be, well, 2 minus 1 is 1 as well. And, well, pretty much anytime I'm integrating just dx between n and n plus 1, I'm getting, well, x between n and n plus 1, which is just n plus 1 minus n, which is just equal to 1. So each and every one of those integrals is just gonna evaluate to 1. That's gonna be 1, that's gonna be 1, and that's gonna be a 1 as well. So what we're left with is pretty much just a sum of those infinite sums that we have to deal with right now. So let me write those, or rather copy those right here. Oh, yeah, I'm gonna be a little bit smarter about it. I'm just gonna copy this entire thing. Yeah, lovely. And I'm just gonna erase those integrals because they are all equal to a 1. Lovely. And now we just have to evaluate those guys out. So how are we supposed to evaluate this infinite sum of infinite sums? Heck, I have no intention of evaluating each and every one of those sums separately, especially as there is infinitely many of them. So we will have to find some kind of a trick. Well, let's maybe try and write down a few first terms of those sequences here. So this is going to be my sequence number 1, this is going to be my sequence number 2, and my sequence number 3. Yeah, so for the sequence number 1, what are going to be the first terms of this sequence? Well, it's going to be equal to 1 plus, and then for n equal to 1 is going to be, I mean, for n equal to 0 is going to be 1 over, well, 2 to the 0 is 1 times 1, 0 plus 1 is just 1, so 1 plus 1 over 2 to the first times 1 plus 1, which is 2 times 2. Then for n equal to 2 is going to be 1 over 2 squared times 2 plus 1, which is 3. Then n equal to 4, 1 over 2 to the power of 4 times 5, times 2. Oh, I should have put 2 here, and 3 here, and 4 here. And it's going to just go on, so on and so forth up to infinity. Now for the second sum, we are not going to get the 1, yeah, but we're going to get 1 over 2 times 2, and then 1 over 2 squared times 3, and then 1 over 2 cubed times 4, because we are starting counting from not n equal to 0, but from n equal to 1. And in the case of the fourth sum, the 3-degree sum, we're gonna, well, also not get the 0th term. We are not gonna get the first term. We're gonna start with the second term, which is 1 over 2 squared times 3, and then we're gonna just be adding all of the remaining terms as it is. But now, well, what is pretty interesting here is that from all of those infinitely many sums, we're gonna get only one unit, only one 1. We're gonna get 2 of those fractions of the form 1 over 2 times 2, but 2 times 1 over 2 times 2, yes, so 2 times 1 over 2 times 2, well, this is just a half. Well, we're gonna get also 3 fractions that look like this, so 1 over 2 squared times 3, but if we add them up together, it's going to be 3 times 1 over 2 squared times 3, but that's just 1 over 2 squared. And I think you know what I'm getting at. Well, each and every one of those terms here, and so on and so forth, well, we're going to get exactly n plus 1 of those fractions. And so we'll actually be able to rewrite this entire sum as just the sum as n goes from 0 to infinity of pretty much n plus 1 divided by 2 to the power of n times n plus 1. But, well, this thing cancels out nicely. It simplifies nicely to just become the sum as n goes from 0 up to infinity of 1 over 2 to the power of n. But this is just a geometric series and we know how to sum it. We know that the sum as n goes from 0 to infinity of some kind of an r to the power of n is just equal to 1 over 1 minus r whenever the absolute value of r is less than 1. Yeah, and well, is the absolute value of a half, which is our common ratio here, less than 1? It is. So we can use this in order to say that this entire thing is just going to nicely evaluate to 1 over 1 minus a half, but this is just a 2, and so we get our final answer, and it turns out that this beautiful monster we had right there is equal to 2. So once again, what did we do here in this problem? First of all, we split the interval on which we were integrating that awfully looking sum into an infinite number of smaller subintervals of length 1 that start with an integer and they also end with an integer. And so then we, well, had the control of what the floor of x in the sigma subscript was actually equal to, and we were able to just take it out of the integral because, well, those sums were not relying on x anymore. We could evaluate our small integrals to just get that each and every one of them was gonna be equal to a 1, and then we just kind of wrote out a few first terms of each sequence there, of each one of the first 3 sequences there, and so a pretty interesting pattern of the fact that when we sum them up, the n plus 1 terms in the denominators are gonna cancel out, and we were left with just a plain old geometric series of 1 to the power of 1 over 2 to the power of n, which was equal to a 2. I hope you guys enjoyed it and see you in the next one.